Okay, I'm going to show you how I would go about answering this particular exam question. So it's from an EDUCAS paper, this one, and it's very similar to the AS specification that you guys will be doing. And it's a pretty good example. It's pretty typical of the sort of thing that your exam board will ask you to do. Okay, so the first one is a simple recall. The exam board wants you to recall the definition that they've given you for a black body in your course notes. So I'm just going to repeat because I remembered it, and that's nice and simply. So a black body is an object which absorbs all frequencies of EM radiation. Okay, I think it's very important that you include the word EM. I also think it's very important that you've got frequencies in there as well. So my next one is a comparison between two stars and comparing their peak wavelengths from their temperature data. So the first thing I'm going to do is I'm going to go to my data sheet and I'm going to find some information out. I'm going to stick it over here to the side, just on the margin, and I'm going to say that lambda max is equal to Wein's constant divided by the temperature. Now Wein's constant, if you remember, is 2.898 times 10 to the minus 3. Now if you don't remember that, that's on your data sheet, so that's there to help you out. Now I'm going to have to do this calculation twice for two different temperatures. So the first one I'm going to do is, let's do Vega first. So Vega's peak wavelength is equal to 2.898 times 10 to the minus 3. Oh, that should be over T, shouldn't it, really? Over 10,000. And I get that to be equal to 2.898 times 10 to the minus 7 meters, or 300 nanometers. Okay, which is, for those of you who have learnt your spectrum ranges, that's in the ultraviolet. Now there's not much room, but I'm going to squeeze it in down here because we know what we're doing now, so it should be nice and quick. So for the sun, the lambda max is equal to 2.898 times 10 to the minus 3 divided by, what's this one? This one's 6,000 for the sun. This information, by the way, is just coming from in the text at the top up here. That one's 6,000. And that is going to give me this time 4.8 times 10 to the minus 7 meters, or roughly, what would we say, 500 nanometers. And if you remember, that's in the visible. It's going to be around green, which is good because you should remember perhaps that the sun produces its peak wavelength in around the green, right in the middle of what we call visible light. Probably some sort of coincidence there. Right, next question. They want me to sketch black body spectra for both of these stars. So the first thing I'm going to do is just note key points. So I'm going to go all the way up to there for that one. I'm going to come all the way, and I'm going to come sort of like here for my other one. So I'm going to take that and I'm going to connect it to my axis like this. And then I'm going to do that one. Now that one, remember, needs to be flatter and smoother. And then I'm going to draw this one, tailing away and flicking off. And then this one, it's very important that it stays under the curve all the way, because they want me, the exam board want me to realise that Vega will have a shorter peak wavelength, so it's going to be more this way, and that it will actually have a higher spectral intensity at that peak wavelength. And it wants me to realise that the sun will always be underneath. have a peak wavelength to the right and be lower than that one's intensity there. Okay, now we've got to flip over to finish off. So here comes the last bit, and now this bit, I'm not going to lie, is pretty tricky, but we're going to use some maths tricks to get ourselves through this. It's no problem. We need an equation to start us off, which is going to go P equals Stefan's constant, which is a sigma, times the surface area of the star, times T to the 4. Okay? Now this is going to get a little bit messy, so feel free to pause, watch what I'm doing, and then stop again. Now we're playing purely at ratios here, so I'm going to start straight out. I'm going to adapt this ever so slightly, so I'm going to say that they've put Vega on the top, so I'm going to use a little v. So I'm going to say the power of Vega is equal to the area of Vega, and the temperature of Vega, over the power of the sun, so a little s for that, Stefan's thingy again, area of the sun, temperature of the sun to the 4. Okay. Now you might have spotted that that's a constant, so we can cross that out. So I now only need to worry about these. I'm going to do a little rearrangement. So I'm going to say that PV, PS is equal to, now area is 4 pi r, so that'd be RV for R Vega squared, times the temperature of Vega to the 4 pi r for the sun squared, times the temperature of Vega to the 4. And cross those out, get rid of that. And then I'm going to keep going. So I know that what the ratio between these two is already, so I can install them in my equation. So PV over PS is equal to 2.71 RS. So I'm going to bring RS up from down here because I know that RV is 2.71 times RS over 1 times RS. But that's going to be squared, isn't it? And the square actually belongs to all of this, guys, okay? So you'll see where I'm going. Don't forget your T4s on the end. Okay, so if we do some tidying up, 1 squared is that, the RS's will cancel, so 1 squared is 1, that will go away, so everything will go away, leaving me with 2.71 squared times T4 right at the end. So I can say that PV is equal to, PS is equal to 2.71 squared times, and I'm going to bring the numbers in from the other side now. So the temperature of Vega, if you remember, is 10,000. The temperature of the sun was 6,000. Don't forget the 4's on the end. Okay, now it goes into the calculator. They come out as two different bits, so 7.344 times this bit solves to be 7.716, which gives me 57. I'm just going to make a statement, therefore Vega 57 times more powerful than sun. Okay, now that was quick, I was pretty furious, so feel free to watch that bit back and try it again yourself. Okay.